My name's Ethan Hoban. I am the president of Eta Kappa Nu, which is the Electrical and Computer Engineering Honor Society here on campus. We host the HKN Tech Talks. HKN is the Greek symbols for Eta Kappa Nu. We host the HKN Tech Talk series every semester. This is the fourth talk of the semester. Our speaker tonight is Chandler Kramer. He's a software engineer out of Alku. I knew him at a prior company, so I'm trying to fix up my mind. Alku, and he'll introduce himself in a moment. But tonight's topic is embedded software engineering, or introduction to embedded software. So let's all give our speaker a round of applause. So use this, get over there just to start, and then just go backwards one to the start.
Okay, cool. Awesome. Thank you for that introduction, Ethan. Like he said, I'm Chandler Kramer, and I'm an embedded software engineer over at Alku. We'll go ahead and go to the next slide. So I am a graduate of UAH with an aerospace engineering degree, graduated quite a few years ago. And I started out my career over at SMAP Center, and where I was doing a lot of war game modeling, some hardware in the loop testing, and doing some launch systems design. And after my time at SMAP Center, I started working at Decibel Research, and that's where I actually met Ethan when I was over at Decibel Research, and we worked together on the GMD weapon system, and I was a software engineer over there. Then after my time there, I decided to join a new company called Alku, and I'm working under a Lockheed Martin contract called the Next Gen Interceptor, where I'm doing embedded software development. This is Ethan's little disclaimer, but yeah, pretty much everything I have is based upon open source information. Any code that you see is stuff that I've written myself, so yeah, there's nothing really of concern here. So what you can expect from this talk tonight is what is embedded software. We're going to kind of cover the basics about embedded software, what's included under that umbrella. And then we're also going to discuss a little bit on the design process for embedded software. So this is going to be a little bit more similar to what you might see in the industry, so you can kind of get an idea of how the process flow actually goes. And then we'll have an in-depth discussion on this little Hello World application that I put together. Then let's see, how to improve upon that application based upon common software design patterns and the principles of embedded software that we'll be going over tonight as well. And then we'll discuss a little bit on how to actually test it, and then hopefully, if we have time, I'll have a short demonstration for everyone. So starting off with the requirements and considerations for embedded software. So the first thing that you need to start thinking about when doing embedded software are a few principles. Number one is going to be about the actual, oh, sorry, I skipped ahead a little bit. So this is kind of more of an introduction of what I'll be covering, just kind of fundamental understanding of embedded software principles, the design process, the software infrastructure that you kind of are going to be using, so things like the tech stack, so VS Code versus IDEs, your CMake versus Makefiles, or Gradle or other build tools, things of that nature. And then we'll also be going over the actual software development cycle and how to execute your software, and among a couple other things. There's going to be a few things I kind of blow through because I do have a lot that I want to cover for everyone tonight, and so I'll kind of try to hit the highlights. And this is going to be one of the highlights, is discussing some of the actual embedded software principles. One of the big things that you're going to be thinking about when doing embedded software is going to be resource awareness. So normally when you're doing software development, you're on these, common computers that we're used to nowadays. When you're doing embedded software, you've got a lot more limits on your resources for memory, RAM, all sorts of different things, timing issues, a whole host of things. And so you want to be aware of your resources when you're doing this type of software development, and we'll be covering that a lot today. And then you also are going to be looking at things like timing and determinism. So you have this concept of interrupts and polling and other things, and this just kind of leads into that next point of performance optimization, because of the resource limitations, you're going to have a lot harder time having things running more smoothly during your runtime operations. And so your performance optimization is going to be very, very important whenever you're developing this software, because there's a lot of tips and tricks that you'll learn tonight that helps with that optimization. Then you also want to start kind of thinking about the layered architecture. This kind of flows into design patterns a little bit, because you've got to start thinking about how you may want an end user to use your application. You have your device drivers, your hardware abstraction layer, and so some of these things are how you're actually going to be talking to the hardware, how your end user is going to be talking to the hardware and interacting with your applications. And then you have things like interface layers that may include, messaging protocols, how you're going to actually send data back and forth between your different registers or something to the tune of that. Maybe it's an external interface as well. So if you're using a radio and a transceiver and a receiver, you'd have something that for that interface layer. And then another thing is reliability and safety. So that's going to be things like error handling. So if something goes wrong critically with your software, you want to be able to catch that. And you also want to be able to debug your software, because embedded systems are notoriously difficult to debug. And so there's a lot of things that you want to kind of cover. And then there's this concept of solid principles. I'm not going to get into that too much, but if you are interested in solid principles, you can just Google them, and a whole host of information will pop up. Next up on principles, there's a lot of them, guys. There's a lot going on with the embedded software. Memory allocation is also another big one. Think dynamic versus static allocation. So when you think dynamic, if you guys are familiar with C++ at all, those are things like standard vectors, standard strings. Those use a type of dynamic allocation. And so that means that it's not a fixed size. So if you have a vector and you want to add something to that vector, it just does it. But what it's doing is at runtime is actually adding to that memory allocation. In embedded, you don't really want that. You can if you're very careful with it, but you don't really want it, because you are pretty much telling the hardware what blocks of memory you'll be using when you're doing your software development. And so you want to stick to static allocation as much as possible, because that tells the hardware, hey, I have this string that's going to be 256 bits or bytes long, and it's never going to be any longer than that. Allocate that memory address and allow me to have that data storage. The next thing, and I'm going to be covering this a little bit tonight, is the testing and observability of it. So this kind of goes back to the safety and reliability principle, is that you want to be able to see what's actually going on with your software as you're developing. It's really important to know that before you actually ship the product, that you know that it works properly. Excuse me, I'm going to take a quick drink of water. All right. And so you want to have a couple different methods in place that allows you to do this observability and this testing kind of on the fly. And so we'll cover this a little bit tonight. State management, that's a little bit in depth on what we're going to be covering tonight, but think flags that tell you when something is or isn't supposed to happen. So if you want a state of like operation mode or different types of modes, you would use something like a state machine. And same thing with lifecycle management, where it just kind of observes the life cycle of like if it completely fails and you need to reset it, your lifecycle management would reboot the software or something of the tune, something to the tune of that. Concurrency, that's going to be interrupts, deadlocks. Again, kind of more of a complex subject that we won't be going over too much tonight, but it's important to be aware of it. Interrupts is basically anything that would stop every other piece of software from doing anything while some other process is happening. And kind of the same thing with deadlocks and priorities. Portability. So there's a couple key. This is more along the lines of good software practices. You want to avoid things like vendor lock-in. So that means if you have a third-party library or something, you kind of want to avoid using third-party libraries as much as possible, because then that's something else that you have to maintain and keep up to date that's included in your software. You may not always want to do that, so you might want to try to find an alternative that you can create in-house. And, you know, some software design principles and patterns that we'll kind of be touching on a little bit more tonight. So, as promised, this is probably going to be the most uneventful and boring part of the entire talk, because this is personally the part of my job that, you know, I like the least, but it's pretty necessary whenever you're going through a full life cycle of a product. And this is just essentially the whole process that you go through when you're trying to design a piece of embedded software. And so number one is defining your requirements. And so this is going to be things like, what hardware are you going to use? How is it supposed to perform? What kind of safety, reliability constraints do we have? And so if you have a specific, you know, CPU, MCU, or sensor in mind, that's kind of where that would start coming into play, because you'd be analyzing things like your timing and your memory constraints. And so if something doesn't necessarily meet your needs, you know, to kind of kick that out right away, rather than trying to wait until, oh shoot, we're using this one MCU and, excuse me, sorry, and it doesn't meet our timing requirements. Excuse me. Then you'll start going into the, excuse me. Then you'll start going into the actual system architecture design. So this is where you might start, you know, determining what your design patterns might look like. So how your different pieces of software might interact with one another, and have kind of a high-level view of how you're going to design things. Your platform definition, that's going to be, you know, okay, now that we've decided what our requirements are, now that we've decided our architecture, okay, let's look at what meets our needs based upon what we've decided. And so that's when you start talking about specifics in hardware. And so you have your STM32s because it has the appropriate amount of pins or ports or whatever. It can be anything that can lead to those hardware decisions. Then you can also start talking about your build system and your tool chain, because now that you've decided on what your hardware is, you can start actually thinking about how you're going to build software for that hardware. And so with STM32, for example, they have an IDE that they ship with their product that you could use. But maybe you don't want to use the IDE because you want to be in control of your build system and your build processes. And so that's when you might start talking about doing CMake and writing your own linker scripts and things of that nature. And so it's really important to have that kind of decided up front so that you're not having to pivot later on. And then again, kind of start going deeper once you have, you know, your architecture design of the software and how all the different components are going to be interacting with each other. You can get a little bit lower level in deciding what your data handling would be. So like that's things like data structures, how you're going to packet the data, what your buffers might look like, if you're going to use message queues and things of that nature. Then you can start having those discussions in that software design phase. And then once you get through that, you start getting to do some fun stuff and start talking about the implementation, where you start deciding on version control, coding standards, and so in unit testing, how you're, or in other forms of testing. And so I'm going to keep moving on. I'm talking a lot. So then you have your actual integration. And so you start putting your pieces together. You start developing a prototype, and you want to see what the integration might look like. And so this starts getting into a phase where you're looking at the different communications and interfaces and how the different sensors actually communicate between the different pieces of hardware. And same thing with the peripheral setup. Then you start talking about your testing and validation. So there's a couple different methods of testing that you're going to go through. And I'll touch a little bit more on these more later tonight. But you have your unit tests, integration tests, systems tests, regression tests, and simulation tests. My personal favorite is the simulation test, but all of them are equally important. And then you start looking at debugging and optimization. That's kind of the last step other than, documentation and actual shipment and deployment. Let's see. So this is kind of a short little spark notes of what to look at with the embedded software infrastructure. So every time you're building embedded software, these are going to be the bits that you're going to need in order to successfully start creating the actual embedded software. So you'll need things like a build system, a linker script, a startup script, source code, and then some type of configuration, your testing and simulation, and the tool chain. So the build system is going to be very similar to, or is going to be the make files, the CMake, or if you're using an IDE, then you're not going to be so concerned with this step. But if you went the route of having the build system fully shipped or fully homebrewed, then that's where you'll start talking about this. Linker scripts, that just kind of tells the hardware how everything's kind of set up. Same thing with the startup script, so that's going to start talking about the setup and initialization of the actual system. Then you will start actually developing the source code once you have those pieces. And then you'll also include the configuration, and that's kind of mixed in with the source code, depending on how you do it, because you can do it in a couple different ways. You can do it in your source code itself, or you can have outside files that you read in with your software using things like JSON or XML, and you can read those into your source code and configure the system, or you can have a header file or something of the tune of that to do it. Testing and simulation, that's where you start looking at unit tests and hardware in the loop stuff. Any of you guys familiar with like concepts like hardware in the loop, software in the loop, anything like that? Yeah. And so that's actually where I find a lot of the fun to be had, is when you start actually looking at the testing of the software, because you get to see it actually working. And so we'll cover that a lot tonight. Then the tool chain is pretty important, but I'm not going to cover it too much. But you will have different build targets and different systems that you may want to build on. So for example, Linux versus Windows. That's where you kind of start thinking about, okay, what compiler am I using? So for embedded purposes, you're usually going to be using a very special kind of compiler that is different than what you're going to be used to seeing. And for example, I think I'll go over more a little bit later. So now that I've bored you guys to sleep with all that, I'm going to give us a prompt and kind of show you guys how you might go about just spitballing requirements and then going straight into an actual example. And so for this particular Hello World application that I'll be showing you guys, this is the problem statement that we have. It's microcontrollers do not have a native firmware support for logging to serial output devices. And we want that because we want immediate feedback from our software. We want to be able to see what's going on. And so you want to have some type of logger so that you can, analyze during and post processing of your code. And so you want something like this. And so what you're going to then have after having a problem statement, you decide what your goals are going to be. So for this particular problem statement, we're going to want to design and develop software that can deploy onto multiple target hardware devices and allow us to read the serial output. And in order to do this, we determine some project requirements. And so we go ahead and lock into the STM32. It's just a different kind of MCU than, is similar to Arduino's ESP32s and other things like that. And that, if you guys remember, the portability principle, that will requirement succeeds that principle because we have the intent to deploy to other targets. So when we're writing our software, we have to kind of keep that in mind. And then we're going to prioritize runtime performance over compile time. So that's going to be a big thing with the resource awareness. And so we're kind of baking in our embedded principles into our requirements so that we know, hey, if I'm not meeting this, then I'm breaking my project requirements, so I may need to rethink how I'm approaching things. And so you have to keep these requirements in mind as you're developing your code. And we're also going to limit the size of the binary of the flash executable, and we'll want to be able to test the software to ensure proper performance and avoid a tightly coupled design. That's going to be your worst nightmare in software. If everything's very tightly coupled, it becomes a real big headache. So now that we've gone over all the boring stuff, we can kind of get into the actual development cycle. And so I start out with the prototyping stage. So first thing I always like to do is I create a couple files and I set up a CMake script. And so this is just a quick and dirty look at what a CMake script might actually look like. And it seems I accidentally pushed it down a little bit too far below, but this is just a quick example. I'm not going to go over this for very long, but this is what it might look like. And what this does is it'll actually generate all the make files for me based upon how I have it configured, and then it allows me to build my project and be able to execute my software based upon the inputs that I give this CMake script. And you can also wrap certain things around it. So if I get to the demo tonight, you guys will see that I actually have a bash script that I use that runs my CMake commands, because I get a little lazy and my CMake commands can get a little long. So I just wrap it up into a build script and run it that way. I find it a lot easier. And I note that there's a couple different alternatives available for different programming languages. So I choose C++. That's just my home base. That's where I feel the most comfortable in when it comes to programming languages. But you can use other things for embedded. It can get a little tougher, but you can use things like Rust. You might be able to use Java. I don't know why you would, but you might be able to. Let's see. Okay, so this is the linker script. So this actually will tell the hardware where things in memory are going to be stored. So again, not going to go too much in depth on this, but if you're going bare metal embedded programming, you need a linker script to tell your hardware where things are going to be in memory. Startup script, kind of similar to the linker script in the sense of it tells the hardware what it's actually going to do. So this is actually written in assembly, gross. And what it tells the hardware is that its entry points and what type of initialization steps that it needs to run whenever you are starting up your hardware. So that's what down here, this system init and the main is saying in the reset handler. So that's essentially telling the hardware, hey, when you start up, hit the system init. When you get done with that, start running our main application. And now we start getting into the real software that you're going to be writing. So this is going to be all the logic that you're going to actually be utilizing. And so step number one for embedded software is defining pretty much where everything's at in memory. So you're going to get that from your data sheet based upon whatever hardware you use. So this is going to be specific to the STM32F407, I believe. And so you can find those data sheets on whatever hardware you're using. And this is just the particular offsets and base addresses that you're going to find in those data sheets. And so this allows you to access these different registers, is what they're called. And so you have your base address up here. And so that's going to be your memory address for the USR2 on the APB1 bus. And then you have, these different offsets for the different pieces of the registers. And so you have your status register offset, your data register offset, I believe that's the baud rate register offset, and some other things, right? All that's in the data sheet. And so the status register and the data register are kind of the pieces that we'll be actually interacting with the most tonight. because that's where things that get stored, like bytes of data and stuff like that, can get placed and then read off of, and things of that nature. Yeah, okay. This keeps happening. This will be happening all night tonight, so sorry about that. But so this is kind of a continuation of our hardware abstraction layer that I started off earlier with on the memory maps. And so this is going to be how you actually start interacting with the different registers. Yeah, you're not going to be able to tell what's going on here because it's garbage, and that's kind of what I wanted to show you guys tonight, of the importance of the design patterns, the importance of how we're going to eventually transform our code into some mumbled, mess into something that's actually readable and easy to follow. Because here, I'm not going to be doing anything different than what I'm going to be doing later, but it's really hard to see what's going on here because I'm using what's called magic numbers all over the place. You don't know what ends and ports I'm setting. You don't know if I'm clearing a bit. You don't know if I'm setting a bit. It's kind of hard to tell because it's pretty complicated code. It's not easy to follow when you don't know what's going on. And the purpose of tonight is to kind of show, even if you don't know exactly what's going on, with a good design pattern and a good foundation in the software, it's a lot easier to at least kind of muddle your way through it and understand what the processes are going to look like. Because here, all this code does is, you'll see down here, I'm just printing out bytes. That's all I'm doing. All this code is just purely to print out bytes to the screen. It's not easy to tell us directly from there. And so I might skip over this a little bit quicker than the other bits because I don't actually use it in the prototype, but eventually I'm going to implement a logger, which is going to actually be our application layer over our previous UART writing. And so the concept here is that you essentially wrap the writes and some of the inits and some of the prints you wrap them in these logger classes, so the interface for the end user is a little bit cleaner to interact with, and it's a little bit more straightforward. And so keep in mind the concept of this logger for the application layer. And then here's what our actual main application. And so this is all it's doing, right, is we have our system in it. I touched on that a little bit prior to, but this is just going to set up the clocks for your hardware. I'm not going to get too much into that, but that's essentially all it's going to do. It's going to set up the clocks and allow us to actually use our hardware because it knows, hey, I'm turned on, I'm ready to go. And then you initialize it in your main function, and then all we're going to do is print tick to the screen. And so we hit our while loop, and every, whatever this is, I think that's probably 10 seconds or so. So every 1 to 10 seconds, we're hitting a tick just constantly. And it's printing it to the screen, and this works perfectly fine, but it's terrible to read. It's really not great. And so now we're going to go into the next step of the software updates. So once we get into here, we start looking at the pros and cons of all of our design decisions thus far. And so for our current memory map, the pros that we have with it that meet our requirements are, hey, we have our compile time definitions. So we don't have to worry about any statically or dynamically allocated memory that we're not expecting. And it's going to be a small executable size because it's all, just simple pound defines. It doesn't take up a whole lot of space. But it's really difficult to read. And you repeat the same thing over and over and over again. And it's really not fun to write because there's hundreds and hundreds of these different registers and offsets that you're going to have to continuously write. And the final bit is that it's globally accessible. You don't typically want that. Anybody can go in and alter what's in those different data registers and when you have things globally accessible. You don't want that because then you have room for malicious actors. You have room for race conditions that you may not be expecting and things of that nature. And so now we can talk about some improvements that we can make on it. And so let's think about adding type safety, maybe some common functionality across the registers, right? So I had some set clears and reads in my previous slides, and they weren't super clear what was happening there, but every data register is going to have that functionality. So you want to be able to add that into some type of class structure, some type of data object or whatever, in order to add some commonality between your registers. And also let's modernize the approach, because pound defines are not great. They're old school. They're fine. I don't have any problems against pound defines, but I prefer using. You guys will see that in just a little bit. But so from our improvements, this is kind of going to be what we're going to look at next, right? So this is what, in an ideal world, is going to change about our current layers. And so we have our base address, and then we have our offsets, and then we have a register that's going to have these different functions in it, and it's going to take in those base addresses and that offset, and then it defines that status register simply by implementing almost the exact same thing that we were seeing earlier, where we have our bus address and then we have our offset, and so now we can easily access this data register, or status register in this case. And then let's start looking at the HAL driver improvements. So again, pros, we got some lightweight definitions with our current HAL driver, and we have no dependencies, but kind of similar to the previous one. It's still globally accessible. It's pretty difficult to read, not very portable, not very maintainable. All really bad things in common software design practices, especially in embedded systems. And so now we want to start thinking about how we can improve that. So we look at implementing classes to allow for better portability. We implement structs that contain some of the characteristics that you may be using, and it adds to the readability of the code. And then you create a generic base class so that you can easily implement any other kind of memory layout that's going to be similar to that current structure. So in this case, I'm going to show how, I think I have the UART example up next. We can go ahead and look at it. Right, so you're going to have a bunch of different UART ports that you can look at. And so same thing with GPIO and whatever, and all of these are going to have very similar functionality across the board. And so you want to have something that you can use in order to maintain that commonality between them. And so here we're going to have some traits that include the pin locations and the addresses. The UART class is actually going to take in those traits. It's going to have an init function, enable clock, and some other stuff. Some other things that you'll get from the data sheet that's going to tell you like how the system's actually going to interact with everything. And then you have your actual implementation. So now, whenever we want our USART2 actually created, we're going to have a UART class call to the USART traits class as a parameter, and it creates that object for us, and then we're able to actually initialize and utilize it. And then we get to the logger and the logger improvements. So pros of the current logger that I don't actually use is the interfacing layer, and it's easy to use. Both of those things are true, but it's a hard-coded backend, right? So I hard-coded using the USART2 port for the current logger, and you want to be able to use different backends if in a perfect world, or have multiple different types of loggers. And so, because you might be using different things like JTAG, you may be using USART1 instead of USART2, and things of that nature. So you don't want to hard code the backend, so it has some flexibility. We didn't have any log level handling there, so something gets printed to the screen. You don't know if it's just printing it just cause, or if there's a critical error, or if there's a fatal error, or anything like that. So you want to add some log handling so that you know how severe the error is that you're looking at. And it's pretty limited extensibility, kind of similar to the hard-coded backend. I'm going to speed it up a little bit because we're at 8:06. And so here I actually implement something called a command pattern. And so what that does is it implements a queue. And so we have a message queue that we now are going to start maintaining. And we have a logger backend, and then we have our command class. And then we'll have a log message command class that inherits from that command class. And same thing here with the logger, inheriting from the logger backend, or it might use the backend. I'll have to look at that in a second. And then this is the actual process events for that command pattern. So it starts at the logger where we have a log message request. The logger would then add the message to the queue. The log message command will handle the message, and then our backend will actually execute the logic. And so that's, really streamlined flow, and using the queue allows us to prevent any type of race conditions and undetermined behavior and things of that nature. So with these new improvements, what have we done so far? It's like, okay, we have our implemented abstraction pattern to the memory map. I'm sure that's a bunch of gobbledygook to you guys right now, but what this does is it introduces type safety. So we have some layers of abstraction that allow us to have this type safety so that different actors can't interact with the wrong types of data registers. And it allows for some extensibility, so we can easily add other ports, other layouts, and things of that nature. We implemented the traits and other patterns to HAL drivers. I really did a hybrid design pattern with this one, but the traits pattern is kind of the most important one of the different traits that we did. And so what we did here was we introduced the static polymorphism, so that's compile time abstraction versus runtime abstraction. The key difference between that is the runtime abstraction is going to be using things like virtual tables and things that are going to mess with the memory during runtime, reducing performance, potentially causing memory overflows, or just a lot of undefined behavior if you're not careful with handling that type of stuff. With compile time abstraction, it all happens at compile time. So if something bad happens, it happens before your software ever gets shipped. And then, the command pattern to the logger, I kind of went over that, and so I'll just kind of skip over into the next slide. And so now we get to the not so final design. If any of you guys have written any software before, you know that you're never happy with your final product, and you always want to improve it because you have a new idea that's going to make it better, and then it will subsequently break. So here we have our memory map update. I'll kind of run through it really quickly. And so, because it gets really deep into C++ territory, and I don't want to bore you guys to death with C++, but I have some resources at the end of the seminar that will allow you guys to dive a little deeper if you want to. So here I introduce some templates and some template structures. And so what I can do here is I can actually place in the memory address or offset into these structures. And then that will create its own type at compile time. And so anytime it sees something that is related to that parameter, it will throw up a type safety check, essentially. And then we have our register here that will now take in our base and our modifier, which is just the offset. And it'll do pretty much all the same stuff that we were doing earlier, but you'll notice that I actually added it as a struct, and we have a couple of common functions in here that will make our code a lot more readable. And so we take in our base address, we take in our modifier, and whenever we create these types now, they automatically get this functionality to be a part of that type. And so now, this is how it looks when we actually create the objects. And it's a lot cleaner than having the straight hex code at the end of the defines. And so you have your USArt, we'll just look at that status register that then takes in our different registered parameters, and it takes in that bus and that offset, and now you have your USArt status register capable of handling any write, read, clear, set operations. These are the updates that we made to the UART driver. So I'll start down here again. And so now we have our struct, and it is going to contain a couple different elements of it. So these are going to be all the different traits. So this is going to be things like pin locations. And so I'll explain what this does a little bit, right? So this is what's called a bit shift. And so that is a shift this bit into the 7th pin, essentially, right? So we are now switching the 7th byte, or 7th bit. So we're shifting the 1, so this could be a 0, 1, or whatever. So we're shifting this value into this bit location. And that's going to be important when you start looking at data sheets, because that's going to enable the different functionality of the different ports. Then we'll have our different UARTs that we can start implementing. And so this takes in a template parameter that will be one of these different traits. And so those traits get implemented or get injected into our UART class, and then it will give it this different type of functionality. And there's a bunch of stuff that I'm not showing as well, but in the end, if we had a USART1 traits, we'd be able to implement the same thing and gain all the same functionality that the USART2 is going to have. And then we also have, I think this might be the other functionality that I was talking about. No, this is the functionality inside of the UART class. And so now every object that is generated using this this UART class is going to have these write and print, thus giving us the availability to implement them into our logger. And then this is going to be our logger backend, where we have the implementation of the logger, and that's going to take in something, I believe that is going to take in our UART class. And then we have our command, and so this is just a virtual, basically an interface class, which is, again, a little deeper into the C++ realm, but you implement that and you inherit it into the log message command class, and that allows us to start calling this execute function, which is going to aid the logger out. And then that logger backend gets injected into our logger and allows us to be able to print to the screen. Let's see. Oh, my bad on the slide on this one. This is supposed to be the main. What's that?
Man over there, I think got a question.
All right, just could you go back?
Yeah, sure thing.
One more.
One more.
Okay. That's all. Okay, thank you.
All right. So this is actually our main function. So this is what gets executed every time we hit our resets. And so we still have the same system in it, or at least a similar one. But you can kind of tell it's a lot easier to read. Of course, not in this format. But you can have a little bit of a better idea on how it actually operates, right? Because now you can look at this code. We're in our main. It's like, okay, we initialize our system. Okay, I'm creating a logger. Okay, I am logging this message. All right, I am enabling the clock. I'm enabling our transaction and receipt, and I'm also implementing a USART1. We're initializing that. We hit a timer, and now we go through our while loop, which is our main loop, and I'm simply sending some heartbeats, and it's a lot easier to read with our new design, right? It's not quite as intimidating as previously, where you're just seeing all these numbers, you're seeing all these, arrows and ampersands and other things that you just, if you don't know C++, you don't know what that's doing. But with this, it's a lot easier to implement if you're coming off the street and using it as a back-end user. And so what's next after that? So that is our full successful run of our UART device doing our logging. And so let's say you want to expand on your current pattern. What would you do next? Next, you would probably start implementing some timers. I implemented a small timer. It wasn't anything crazy. It just does a couple ticks. But you'd want to start implementing timers so you can start executing different pieces of software at particular times and at particular intervals. You might want to add interrupts. So something happens that causes your system to stop, and you want this piece of software to run now. So you can start adding interrupts to where, let's say, you're sending a message from one sensor, but you want to get a message from a different sensor, and that sensor has priority. So this sensor would then inject its message into the system, trigger the interrupt, and stop all communications with this sensor until this new function completes. Maybe you want to start implementing new sensors. So yeah, start implementing some IMUs, start implementing whatever you want, and have some fun with it, right? Start reading the data back to the screen. Plug in an IMU, hook it up to your device and see what it prints out back to you on the screen. That would be the next step as well. Actuators, maybe you want to start telling a servo motor to move up and down. You can start doing that now too. Same thing with data communication. You want to start doing external communication to other devices. You can set up your new embedded system to send data back to your computer. Super easy to do. And let's say you want to get real crazy with it and you want to start implementing an Internet of Things device. So that would be hooking up multiple MCUs doing multiple different things and distributing the workload. You can do all sorts of things to expand just from this simple example. You can start really digging into a lot of fun stuff because you've done all the hard stuff already. You got a couple design patterns up and you're ready to start implementing new things. So now let's get into the testing part of things. I'll go a little fast over this section because this is mainly what my demo is gonna cover. So for testing, you have unit tests, integration tests, system tests, regression tests, and simulation tests. Those all serve different purposes. Unit tests are pretty granular, but they don't provide a whole lot of feedback on how the system works as a whole. Integration test gives you a little bit more insight on how the system might work together. Systems test is the full integration of the system and seeing how it works. Regression testing is going to be something that you might set up in a pipeline, CI/CD servers or anything like that, and automatically execute every single time that you push new code to the server. And then simulation tests, this is what I'm going to be showing in just a minute, where you start implementing simulation frameworks and hardware to see how your stuff actually works. So I think I'm going to skip over the rest of this stuff and show the demo. I think that would be a lot more fun. And so this is just a quick snippet of what you guys are about to see. Yep, let's go ahead and get right to it.
And the slide deck in full will be sent out to everyone who fills out the exit form. So if you want to review these things more closely and try them out for yourself, you'll be able to.
Yeah, I think that'd be good because I added a lot of resources at the end as well that provide some learning resources to open source options. And so here we have the actual code.
It might be worth zooming in a bit.
Oh yeah. Yes. All right, so I talked a little bit about the build script, and so I don't know how familiar you guys are with things like Bash and other things, but it's really easy to implement a build script into any system and use that to do some common tasks and give it some different different functionality. And so here I just have two little commands that I can do. I can do my build and I can do my emulation. And it just does a couple different functions. I mean, it's a really short script and it saves a lot of pain because you can kind of see how long these build commands can get. And having to do that every single time really grinds my gears. So if I were to run this command, what this is actually going to do is it's going to execute my, so it's going to first flash my software onto my hardware, which is in an emulated environment. I'm not sure if I can zoom too much in on this, but so first step it does is it actually flashes the software onto the hardware, which is just emulated by the software I'm using called Renode. And this allows me to actually see the fruits of my labor and tell if I am doing things correctly. And so I'm constantly getting these heartbeat intervals that are just, periodically telling me, hey, I'm still going, I'm ready for you. And so let's say now I want to send a command into it. And so I believe it is, so I actually have it set up to where I have my USArt1 passing in information into its data register. And then my logger is actually using the USArt2 as the backend, and then we'll read the bytes of data that I'm sending it off of that data register and then print it out to the screen. And so if I do introduction to embedded systems, I've never tried a message that long, but hey, it worked. And so I just sent in my command over into my USArt1 data registry, and it was read off of its data registry by my USArt2 backend logger. And tells you an introduction to embedded systems. And so that's about all I got for you guys tonight. And so I think I'm going to shut that down. I'll switch back over to the PC. And yeah, we'll open up the floor for any questions.
All right. Everyone give it up for. I know y'all have questions, so go at it.
Yes.
So you made your own hardware abstraction layer, right?
Uh-huh. Yep.
So I know that ST, ESP, Espressif, and all of them have their own hardware abstraction layers.
Yep.
Why not use those? Is it like, would you only use it for like rapid prototyping, or is it like an optimization thing?
It could be a couple of different reasons, right? One of them could be for rapid prototyping. So if you only wanted to grab a couple of those data registers and put something on real quick, you could just rapid prototype it. But if you're doing something more full scale, you may want to use those hardware abstraction layers that they ship with it. But it's also a kind of a customization / learning experience, right? So maybe you want to learn how those hardware abstraction layers work. And so you can, go and write your own and figure out how to read a data sheet, how to put something together and use it. Or maybe you don't like the interface and the API that they use, right? Maybe you want to design your own interface to that hardware abstraction layer. And that's how you would do that. And it could be an optimization thing too, because maybe you don't need everything that they ship with their hardware abstraction layer. And so you want to reduce that binary size. The best way to do that is reduce the number of registers that are included in that hardware abstraction layer.
I will also note they don't ship HALs for every single chip. Like STM32, there are like enterprise prototype boards that they'll ship stuff for, and they have environments to support. But STM and Espressif make like hundreds, if not thousands, of variants for their chips, and not all of them have them. And as Chandler said, there's a lot of optimization that takes place. It's extremely rare that you need every single register. Often you'll need like 10.
Yep. Yeah. And it's also worth noting that a lot of times in industry, you're using custom hardware too. Like if you're in at Lockheed Martin or over at Northrop, you might not even be using like a commercial off-the-shelf chip.
We make our own chips.
You typically make your own chips, and so you'd have to make your own hardware abstraction layers for that purpose as well. Yes.
You said for embedded systems, there's a lot of limit on memory. So how do you deal with that constraint while programming?
Okay, good. So that's where a lot of the optimization layers start coming in, right? Because the different ways that you do your programming change the way that memory is being handled. So one of the big ways is using those, constrained size strings and arrays, and you limit the size of those bytes, but you can also use things like pointers and addresses. And so instead of doing direct copies and direct, copies is really the best way of doing it, or not doing it. Because if you're doing a copy, you're now reserving a new slot of memory every single time you're doing that copy. So if you start using pointers and addresses, that is one way to avoid any type of overhead with memory. Anything else?
Is everyone familiar with like the type of memory restrictions when Chandler says like an embedded systems memory restriction? So does everyone understand like on the order of how much smaller we're talking compared to like your laptop? Yeah, on the order, your laptop might have gigabytes available. Often, at best, you have kilobytes available of dynamic memory and maybe a megabyte or two of static.
Yeah. Same thing with RAM too, right?
Oh yeah, you literally, that's kilobytes.
Yeah.
It's bad.
Yeah. You had a question?
Well, y'all kind of answered it.
Oh, okay.
Doesn't have to be about the presentation. You can
No.
also ask about career concepts,
Yeah.
tips and tricks,
Yeah.
all the good
Feel
work. This is a man who is an aerospace engineer who's now the software god. Think about that.
Hardly. Yeah.
Yeah, so I know you were using VS Code for this one, but
Yep.
do y'all have a, at least where you're working, do y'all have a standard, or does it change for what IDE y'all are using, or what?
So for the most part, most of the time you're not really using an IDE. I use VS Code mostly as a text editor. You can add some extensions and stuff like that to where it becomes kind of a full-fledged IDE. For the most part, you're going to be designing your own build systems, and so you can have kind of the pick of the litter. I know people that straight up code in Vim and and Nano and things. At my current job, the onboarding process was quite lengthy, and for the first 2 weeks, I was completely doing terminal programming, Nano, Nano and Bash. That was my life. For a couple of weeks, and it can be done. It's not very optimal, but for the most part in the industry, you're going to be seeing own build systems, and usually VS Code is the default text editor. But you can usually use whatever you
So
want.
you kind of use VS Code as like for the IntelliSense, and then
Yep.
just kind of use terminal command prompt for
Yep.
everything else. That's what I've been doing.
Yep,
I just use Visual Studio though, so.
that's my preferred way of doing it, because
You don't have to fight VS Code to get it done.
yeah.
Just do it with the terminal.
Yep, precisely. That's why, I really like making CMake scripts, CMake lists, and things of that nature. Build scripts. I love Bash. One of these days, how many of you guys know Python or use Python? Right. One of these days, you guys will become a Bash connoisseur for most common tasks, because it's usually better for system level commands. If you guys have ever tried to do a system level command in Python, it's kind of gross. And so if you want to do system level logic, usually Bash is the way to go. And that's usually what I use mostly for Python. But Python is still king when it comes to string parsing. I will say that, because string parsing is one of the layers of hell.
Next slide.
Yeah, I don't think, oh, yeah, sure.
Yeah, you
Yeah.
got stuff.
Yeah, I guess so. So if you guys are interested in learning some more, I added just some resources that could kind of help you get further along. And so one thing I always tell up-and-coming programmers is go to projecteuler.net. It has a whole bunch of, this guy knows Project Euler, Euler, sorry. So there's a whole bunch of prompts. They're all math-based, and they really help you understand the optimization of programming. I think the first time I did the Fibonacci sequence, it took me like 30 seconds to do like 100 Fibonacci sequences, which is not good, right? You can do it way faster. But when you're learning code, I don't think there's a better way to do it than going to Project Euler. Refactoring Guru has so many good resources on design patterns. And so anytime you're curious about, all right, I make code this one way, how can I kind of improve it? There's usually a design pattern for that. And Free Code Camp, I like Free Code Camp. There's nothing wrong with it. It has a lot of really good material on its website. I recommend checking it out. Then these are just kind of resources to the more embedded focused things. And so Renode was the simulator that I used today. So you can go check out its documentation. It is not great. So forewarning. And then there's some forums and stuff like that. So this is the compiler that I use for the STM32. And so it's an ARM compiler, and on its home page, it has a whole bunch of resources for learning and different forums that you can go in and see what other people are doing. This is a link to STM32. You can go find data sheets on there on just about anything. I didn't touch on real-time operating systems too much, but if you guys are interested in learning about what a real-time operating system is, FreeRTOS is just about the only free version you can get, but it's completely open source, and it's a good resource. And then, I just wanted to throw this down in here. If you guys have ever thought about contributing to open source projects or anything like that, you can go to this code triage, and it will slap you in the face with how many different open source projects there are out there that you can contribute to as early as tonight if you wanted to, because there's all sorts of bug reports and stuff like that, simple fixes that these different projects might have. So feel free to go poke around in there and see if you want anything to do with that. And then this is just some good books that you guys might be interested in. This is still the best design patterns book ever written, and it was written actually before I was born, so which is kind of crazy. And yeah, just some more information on different resources I used. This book, The Embedded Systems Architecture, also a really good book on, it really dives in deep into things like the linker script, startup scripts, and hardware abstraction layers, all types of stuff. That's where I actually learned quite a few things, and so definitely check it out. And that's it.
This is how you get the slide deck. And one note, so with regards to the simulator, it's annoying to use, as Chandler has figured out for us.
Yeah.
But your options are, if you have a team and you're working on a project that's meant to be embedded and you're all working on different portions, your options are buy a board for each person or simulate it for free. So those are your two options.
Yeah.
And it can get pretty hectic, so it's rather important to really consider the validity of simulation of the hardware itself.
If you want to get real crazy with it, you can design your own simulation framework.
You can.
Yeah.
You can. You want to show them the memory map?
Yeah, I can show them the memory map.
Has everyone gotten the link? Good. He's going to traumatize y'all now. By the way, the code that Chandler is showing is actual code from a project that I have him helping with. He's the GOAT.
Yeah, so if you guys have ever wondered how fun this was,
There's a lot of registers.
there's a lot of registers. So the data sheets are thousands of pages long, and each register has its own base address and a list of offsets for where stuff lives in memory, and it just keeps going. But before this, let me see if I can, I don't think I have any. Yeah, good.
Use tag.
I think I can just do it. Actually, I do think I can do that. Oh, no, it's. So this is what it was before I made the changes, which I feel, in my personal opinion, this is more gross. because you have all these different casts and you have these different pointers and traumatizing really is what it was. And so, yeah, this is how it started out. And then same thing with kind of the UR. The UR was kind of garbage to begin with. But
You can see how if you're not making use of every single functionality on a piece of hardware, why you might want to make some modifications from
Yeah.
a space saving perspective. Particularly as you start shrinking your hardware down, we're talking
Yeah.
your total flash could be on the order of actual kilobytes.
Yeah.
So you need to be
and
rather careful.
Yeah, and so now with the new design, this is what the full USR2 trace actually looks like. And so I define all the different pin operations that you might have, and then you can just slap the using statements into the actual traits themselves. And now you can actually pass that into, have a good one, guys. You can pass that into this template type. Yep.
All right.
Cool. All right. Well,
Let's hear it up for Chandler one last time. Thank you all for coming. I hope you gained something. It's a very deep topic. It's really hard to actually take you from 0 to hero on a single go, but I think Chandler did a fairly good job getting you started. And I'll send out all those slides to everyone to fill out the sign-out form. We have 2 more tech talks. They're on a bi-weekly cadence, same place, same time, same day, every week, every other week. So the next one is 2 weeks from now. And the next talk is, I believe it is UAV design. So we'll be doing small unmanned aerial vehicle systems. That'll be Cummings aerospace engineer Sean Mitchell. He's worked on several, but his company has a flagship system, loitering munitions. Think of it as a 3D printed cruise missile. Right? So he's got some good experience on that. And then our final talk of the semester will be Jacob. Oh, I forget my own boy.
Hicks.
Yeah, Jacob Hicks, former Lockheed Martin engineer, and he'll be doing satellite communications. So he'll be breaking down how that works, how you can get into it from a software level, software-defined radio, that kind of stuff, satellite hacking, that kind of thing. All right. Thank you all for coming.
On behalf of Jackson Lawrence's class, thank you.